the rain, or I really have to fight all the sounds. Okay? Alright, so this is how we sort the elements, compounds, and mixtures. I hope you can see by now why we sorted this way. Okay? Notice that, to recap, elements, let's look at elements. You look at each box, you notice that it's the same type of atoms. Regardless of whether it is a single atom by themselves or the atoms are joined together to form something starts with an M. Molecules. When you have more than one atom joined together, same or not, we refer them to molecule. Okay? So if you look at all four boxes, what's similar between all four is that you only have one type of atom. Whether it's molecule or atoms by themselves, it's just same type. And that is what we refer to as an element. Look at compounds. You see that compounds, each box, you find that they are chemically combined in the same proportion. Whether it's this one, this one, or this one, or this one, it's always one white one to four small black ones. Always the same ratio. Over here, same ratio of the black one, polka dot one, and the white one. Black one, polka dot one, white one. Same ratio, same ratio, same ratio. Another thing in common is that they are always molecules. Right? You do not find any compound that is just an atom by itself. Then we refer to it as an element. So here, molecule, 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 molecule. Just that this molecule is made up of how many atoms? 5 atoms. This molecule is made up of 3. This one, 2. This one, 3. This molecule is made up of 2 atoms. This one, 2. This one, what? 2, okay, 2, 2. Is this a molecule? No, they are just atoms. Last but not least, when we look at mixtures, you find that, hey, actually it's just really, as you know what mixtures are, just a mixture of things. You look at this, you look at this one box, you find that it's already a combination of many things. You find that there's one type of compound here, and there's another type of compound here. It's a mixture of 2 compounds. This is a mixture of, how will you use the terms that you learned so far to describe this? It is a mixture of how many compounds, how many elements? Okay, many ways for you to describe this. I heard this is a mixture of, mixture of atoms and molecules. Okay, that's one way to describe this. Any other way to describe this? Mixture of, sorry? It is a mixture of elements and compounds. That's fair. How many elements are there in here?
1.
Oh, okay. So, okay, now that is a good point. Technically, you could say that there are 3 types of elements you can see here. There is the black one, there is the white one, there is this brick one. Fair enough. There are kind of 3 types of elements present. So, a few ways to describe this now, yeah? But it's not wrong to say this is a mixture of elements and compounds. This is a mixture of, it's a mixture of elements. How many elements? 2 types of elements. This is a mixture of compounds and elements. Okay? So I hope you can differentiate between the 3 at this point in time. Yeah? Last but not least, I think one thing very important for you, all of you, to observe is that when you look at elements and compounds, they are both pure substances. What do I mean by pure? Same type. Look at this box of compound. Notice that they are all the same type of compound. It is pure. But the moment I add something different into the mix, becomes a mixture. So pure substances and mixture, they are different branches of things. Mixtures comprise of a bunch of different things. Could be a mixture of two elements, could be a mixture of two compounds, could be a mixture of compounds and elements. Pure substances, however, we are looking at just one type of thing. Either a pure compound or pure element. Your flow chart inside your textbook should show something quite similar. This is where we are at. We are not looking at this. We expect you to know this from primary school. But now at this stage, we're learning a new way of classifying matter. And we can look at matter in the form of mixtures or pure substances. And now we are down these two branches, elements and compounds. And I think at this point in time, you're getting stronger in the skill of differentiating if I provide you diagrams. Okay? Yeah, listen up. Yesterday I showed you this, an example of an equation. On the left hand side, we show you two different elements. On the right hand side, we show you a compound written in words. Usually compounds, when written in words, you can see that it comprises of both elements' names. So make sure you have your textbook open there. Today, I got these three items. I have iron, I have sulfur with me, and I also have iron sulfide. I'd like to pass them around, let you have a look at what real elements and real compounds look like. Don't open the sample up, okay? Yeah, I'm going to pass them around in sets. So, this is one set. In this set, you can see there I have a mixture of sulfur and iron. Sulfur is the yellow one. Okay? Sulfur as element is yellow in color. I also have iron inside. You all may recognize it as the black powder. Over here, I have iron sulfide on the left hand side. On top of that, I'm going to pass around a magnet. Okay, I have two magnets I'm passing around. Do not remove the metal parts of the magnet. Okay? Leave it on. What is the magnet for? I want you to experience this for yourself. When you look at iron and sulfur, they are both elements, yeah? I purposely chose these two elements because one of them is a metal, the other one is not a metal. Right? When we look at elements, actually we have two kinds of elements, metals and non-metals. For example, oxygen is a non-metal. But if you look at copper, that's a metal. Today I've chosen one metal and one non-metal. A lot of metals have this property. I think you all learned before in primary school. Magnetic. Heard before? Yes, Samuel? Oh, I didn't. So sulfur is this color, yeah? It's not white. Later you see it's yellow color. Yellow powder. Later on, go and experience this for yourself. Yes, Kadir? It does. That's why I closed it up, yeah? Where can you find sulfur sometimes? I think it's present in eggs, hot springs. That's where a lot of smell. Your fart also sometimes contains a sulfur. So it does have a smell, a very pungent smell. Later I'll take a magnet because one of the elements in there has a magnetic property. After you test it out on the elements, take the same magnet and test it out on iron sulfide. Iron sulfide, the compound. Go and test it. See if it has the same property as the elements. Alright? So I'm going to pass these three things around. It will take a while to reach you, but when it reaches you, have a go at experiencing it for yourself. Please take good care of the items. It's been taped up at the side. Do not let it open up, okay? Because they are powder. Once it comes out, very hard to contain back. What do you mean the iron plus sulfur? This is the compound version.
Did you know that?
Yes. Okay, so Karen has asked the question, hey, how in the world was iron sulfide made? How come I can have one battery dish that contains both sulfide and iron side by side, mixed up, but they didn't react together to form this compound? Yes. How did I combine it? So, how did I combine it? I need to combine, the only way to combine two elements is if I carry out a chemical reaction. What is a chemical reaction? There are a few ways I can carry out a chemical reaction. Okay, the first way I can carry out chemical reaction is using heat. Sometimes when we apply heat, it can cause two elements or more to react with each other to form a compound. Another way I can carry out chemical reaction is if I apply electricity. Sometimes a little electricity can help to trigger the chemical reaction from occurring. Lastly, sometimes all it takes is for the two elements to mix with each other. Sometimes that's all it takes. If they touch each other, they will react. However, iron and sulfur inside that petri dish, it cannot react with each other just by touching each other. It needs a little bit of help. There are some things that just touch each other can react very fast already, but not all elements can do that. Okay, I will pause a while. Then you find a page to note down the new information.
How about we escape?
From the side, is it?
Like the thing is like
Okay. Yeah, so you try not to shake too much. Sorry?
There's some of them.
It's okay. Just pass it on. Okay, if the magnets end up on the same table, we are request that you do not let the two magnets touch each other. These two magnets are very, very strong. Once it touches, they will influence each other and they will damage each other. Okay, so I need to keep them apart.
The powder is making it full. The powder leak.
What?
That's why you don't shake.
Yes. My dears, the petri dish is not fully sealed. They try to take, but it's still leaking from the side. So try not to shake too much. If it does land on your hand, make sure you keep off that. Don't eat it. You're not done? Okay, so what would be the scope of today's lesson? In today's lesson, we're going to look at the properties of elements and mixtures. scope for today. So far, we are able to differentiate them if I provide you diagrams. But we're going to spend a little bit more time talking a little bit more about their properties. Okay, these are the properties that you cannot see in diagram, but you are expected to know. And you will slowly experience it more and more as we let you handle more chemicals. Yes. Okay, then I'll ask, what does carbon look like? Carbon has two looks. Can look differently depending on how the carbon atoms are joined together. So, one very common carbon that you have seen before in jewelry shops is diamond. That's what one form of carbon looks like. Another way that carbon can look is that it just looks like a black piece of coal. Because another form of carbon is graphite. Graphite is also carbon. You will learn a little bit more in JH3 why carbon can look so different, even though it is the same element. See here? Yes, that is, usually you hear people talk about that, they are referring to a compound version of iron. Okay, where is the specimen now? Okay, so everyone got a rough look at the different elements and compounds. Okay, so let's look at some of the properties of elements and compounds today. Sorry? Give me a go virtual experiment. Yeah? Okay. First and foremost, let's talk about the word pure. What does the word pure mean in the context of chemistry? When we look at chemistry, when we say that something is pure, we mean to say that it has a very distinct property and its composition does not vary. But what does that mean? It means to say, if we will give you a box, whatever is inside this box, if we say the composition does not vary, means that wherever we go within the box, you will find exactly the same thing. Okay? That's what it means by composition does not vary. If the composition varies, it means to say that within a box, you find that at one place you find something, another place you may find something totally different. This means that the composition is not the same across the different parts of the box. Okay? This is not pure. This is a mixture. Okay? Has consistent and predictable properties. Wherever you go in this box, the property of the element will be the same. Wherever you go in the box, the property of the compound may be the same. In my specimen over here, where I have sulfur and iron, this is a mixture. The property here and there everywhere will be slightly different because I have two different elements together. However, here I have a compound of iron sulfide. This is purely iron sulfide. The property in this box is exactly the same everywhere in this iron sulfide. Yeah? So I have a purely compound over here, and in the other box I have a mixture of two elements. And you can expect the properties to be slightly different. We have learned so far that elements and compounds by themselves, they are pure. But you can mix elements and compounds together. Inside the petri dish, we have a mixture of elements. And you are now able to differentiate between diagrams, whether it's a mixture of compounds, mixture of elements, or mixture of elements and compounds. But how do you tell if something is a pure substance if I do not provide you such a diagram? Right? Okay, this is important. How do you tell if a substance is pure? There are two ways to tell. The first way to tell is what you've already been doing. If I provide you a diagram, can you tell if something is pure or not? You just tell by whether it's the same type, correct? So is this pure? Yeah, it is pure. Just purely the same molecule present. But how do you tell if something is pure in real life? Yeah? Because it's not like you have special eyes that can zoom all the way in to see the molecule. So how do you tell in real life if something is pure? Well, scientists can conduct experiments to tell if it's pure. How do we tell if something is pure? You check for its, okay, you learned this in primary school, melting and boiling point. You learned before, huh? Okay. Melting point is when? Okay, the point at which something melts from a solid to liquid. What is the boiling point? Liquid to gas. Okay, so how do you tell if something is pure or not? Actually, pure substances, they will have a fixed melting and boiling point. What do I mean by fixed? No matter how many times you conduct the experiment, the substance will always melt at that temperature. Will always boil at that temperature. I'm going to give you an example that I think you already know about. Water. H2O. Water. Let me represent it in diagram form. You learned in primary school that water's boiling point is 100 degrees Celsius. What is its melting point? Okay, its melting point is same as freezing point, right? Okay, its melting point is 0 degrees Celsius. You know that if water is not pure, let's say if you were to have, let's say you have water and someone tried to mess with you, go and add salt in, or go and add some random chemical in trying to poison you. You know that if you were to try to boil that same cup of water, even though it looks exactly the same, the boiling point will not be 100 anymore. If you try to freeze that water and it becomes ice, and you go and let that contaminated ice cube melt, it will not melt at 0 degrees Celsius anymore. So, substances that are not pure will not have fixed melting boiling points. So that's one way you can test in real life. Okay? So if someone would ask you how to find out in real life whether something is pure, you go and check whether it's a fixed melting and boiling point. If the water is not really pure and it's a mixture of many things, actually the boiling and melting point will change depending on how much of the extra thing I have inside. Okay? Oh, okay. So actually if you add salt inside, depending on how much salt you add the boiling point can also change, right? Pause here for a while. When we start conducting experiments, you can go and test for yourself. When you get water from the tap, and if you are ever asked to boil it, and there's a thermometer inside, if it haven't reached 100 already start boiling hot, or it only boils after 100, that means whatever is coming out from the tap, it's not exactly pure. Thank you. Yes, India. Go. Thank you. Let's take a short mental break. You know you can extract the iron out from your cereal. Yeah. So I'll show you iron cereal. Okay, let's watch this video. You know there's also iron inside your cereal, a little bit. If you want to extract it out, there's actually a way for you to do it. But it needs a little bit of help to extract it out. fill a little bit of water. Usually what we do next is we blend it. Okay, if you want to buy very strong magnets, if I'm not wrong, you know what art friend is? The art friend is art store. There's one section in art friend that sells science stuff. Yeah, some students go and break my test tip hall, then they, if I'm in an angry mood that day, I'll ask them to art friend go and buy the test tip there. So art friend has a whole row of science experiment stuff, and then there's one section that sells magnets also. I think you can buy very strong magnets over there. It is affordable. Yeah. Okay, so a summary of what we've done so far. We talked about pure substances. And when we look at pure substances, we can look at elements of compounds. And today you've seen some real examples also. Here are some examples of elements. You may have heard of them before. This is a picture of some of them. So for example, aluminium. You heard of aluminium before? No. Sorry, I'm looking up for you. Aluminium, the aluminium foil you have at home. Yeah, to say that the aluminium foil you have at home, usually it's not purely aluminium. They usually coat it with some other metal also. Gold is an element. Carbon is an element. This is just one form of carbon. Another form of carbon is diamond. Iron, sulfur, which is what you saw. Zinc, phosphorus, which is red in color. Chlorine. Chlorine is not this glass jar. Chlorine is actually a gas. It is inside this jar. Okay, the chlorine that you have in the swimming pool, that is a liquid form of the chlorine. Chlorine can also exist as a gas. Okay, and the gas form of chlorine is actually yellowish green in color.
They use that chemical weapons. They use that.
No, chlorine exists as a gas. Do you know that every metal on Earth can exist as solid, liquid, and gas? Yeah. It just really depends on how much heat you give it. You know that iron can also get liquid form, right? Yes, yeah. But human is made up of many different elements and compounds. So we are mixture, correct? So that means, if I try to boil you, versus I try to boil Tyson, right? You all will boil a different boiling point. Yeah? Yes. Okay, fair enough though. Isabel, your question? Okay, hold on. Isabel, yeah? How do we know it? Because scientists have managed to extract out chlorine gas by itself, pure chlorine, and you put a transparent gel on, it really looks yellowy. Okay. That's maybe what you taught in primary school, but actually there are some gases that have color. Okay, so I think in primary school they may have told you gas is colorless. Okay, not all gases. Some gases have color. Chlorine is an example, it's yellowish green. Samuel? Okay, I tell you Samuel, what is the opposite? You won't get high, you will die. Okay? Because the chlorine used in the swimming pool. Okay, if I'm not wrong, sorry, I think I have to take it back. So I'm going to take it back. I'm thinking the chlorine that you see in the swimming pool is not pure chlorine, If I'm not wrong, the chlorine has already been reacted with another element to form a compound, and that compound is not poisonous in large amounts to you. Okay, chlorine gas was used as a chemical weapon during wartime in the past. You know what the effect of breathing in chlorine gas is? No lah, chlorine gas is not equal to nuclear. Okay, chlorine gas is yellowish green. Last time, if I'm not wrong, during World War I, when soldiers see a yellowish green gas coming to them, they know that they are in very, very big trouble. Because this gas, once inhaled into you, remember I said some elements, they just need to mix with each other and they can really form a compound. Okay, so chlorine gas, if it mixes, it just touches another element called hydrogen. Okay, so this is chlorine. Okay, hydrogen gas can be found in our atmosphere, right? Okay. When these two don't even need heat, just touch each other, you know what will happen. Okay, you know what you want to make an activated gas? If I mix hydrogen and chlorine together, what do you think is the name of the compound?
Disaster.
No? Samuel, what do you think is the name of the compound?
Hydrogen.
No, it's not called drug.
Hydrogen chloride.
Okay, sorry, Xavier. It is called, this is the chemical symbol of it. This is the name of it. Hydrogen
Chloride acid.
chloride.
Acid.
You know what this is?
The one
This is
from
an
acid
acid.
on
This is in the air. So you know what the soldiers in the past, right? When they did not know that chlorine gas had this effect, they ran out into the battlefield. They take one breath in of the chlorine, and as they take the breath in, along with the hydrogen in air, it forms acids in their lungs, and literally they feel their lungs burning, and they will die because hydrochloric acid is a very strong acid that can burn not only your skin, but can you imagine if you breathe it in, it burns your lungs, and they actually suffocate right there on the battlefield because their lungs get burned on the inside and cannot breathe anymore. It's too late. They did not know the effects. And so ever since then, this gas, right, has been put up by the UN, banned from the battlefield. It is inhumane. Okay? I mean, war is inhumane. Yes, I mean,
Yeah, you said that.
oh, okay. Good question, Tatik asked. If you just breathe in pure chlorine gas without hydrogen, is it harmful? It is still harmful because chlorine in another reaction, if it touches water, can also eventually lead to hydrogen chloride. Okay? So, still possible.
Chlorine is
Yes. Say again.
It can dissolve
Yes.
steel. High explosive.
Oh, but I already said the chlorine in your swimming pool is not this chlorine. Element. It will change its form. The properties will be different.
Magnesium. Polonium.
Yeah. Okay? Yes. Yeah. Yeah. Where did you learn that from? That oxygen increase effect. Oh, okay. I think I used the word burning and okay, so the burning that I'm talking about is acid. I think maybe I shouldn't use the term because it's not really a chemical term. In chemistry, in chemistry when I say burning, I do mean that there's oxygen involved. But earlier on when I said the acid burns, I think I was using it a bit casually. Okay, acid doesn't burn in the way that requires oxygen. When I say it burn, I'm sort of saying that, you know, if you get touched by acid, it looks like you get burned.
Like that.
Okay, a better word for acid effect, right, is called corrode. Acid can corrode. Okay? You all learn as you progress through the various chapters. Yeah? Okay, so we look at the screen. We already mentioned this before. When you look at elements, how do you tell if something is an element if it's the same type of atoms present? It is okay if it is an atom or if it's joined together as a molecule. Okay, here are just some examples. I do not think the examples are in your textbook. If you like to put down some more examples of what other elements can look like, you could write it down. For example, these two elements they often exist as just atoms by themselves floating around. Oxygen as an element could exist as O2, could exist as O3, as someone brought up yesterday, ozone. Hydrogen tends to exist as two joined together to form one molecule. Some of you may be wondering, why do some elements like to be by themselves, just as atoms? Some of them need to find a partner to join with each other. Okay, actually, Anaya is right. It has to do with how reactive the element is. Some elements are not reactive. Okay, even as I use the word reactive, I think it's hard for you to fully comprehend. But usually, if you find elements joined together, existing as molecules, it means that they have some level of reactivity. Those that exist by themselves, usually they don't like to react with anything, so they're by themselves. Yes, I did.
Those that usually exist by themselves are gases.
You're right also. Yeah? Those that exist by themselves as just singular atoms, they tend to be just gases.
They're called normal gases.
Even you learn all this, are you from the future?
I read the O-level textbook.
Oh, okay. Yeah, you're right. But whatever you just said, we only learn when you are in I think JH2? Yes. Okay, Garrett asks, if I mix hydrogen and oxygen, do you get water? Okay, the reality is, remember I said, not all elements you mix together just touch can react already, right?
You use fire.
Hydrogen and oxygen is one example where you just let them mix, it's not going to happen. For example, actually right now in our air, there's both hydrogen and oxygen floating around. But they do not spontaneously join and form water. Yeah? So, how do we form water if we want to make these two react with each other? Electricity. Okay, electricity can help these two elements react with each other, reform and form water. You may also be wondering, how do they react? Okay, if I were to draw it in diagram form, it looks something like that. So here is oxygen. Here is hydrogen. Actually, what's happening when we apply heat or electricity, usually is to help them split up. So for example, if I apply electricity or I apply heat, sometimes what happens is that these two atoms will split up. This will split up, and then they will rejoin, but just a little bit differently. Oh, but you realize the proportion is off, right? So now I have one atom by itself, right? So actually, I will technically need for every oxygen I have, for every oxygen molecule I have, actually I need very good, 2 hydrogen molecules times 2 hydrogen molecules. Okay, so this one will then get to go to this, and after that I can form another water molecule. But you can sort of get a sense of how chemistry is going to be for you all next time. Next time, as you understand more and more, you will actually start to learn about these proportions. If I want to make water, how many oxygen and how many hydrogen molecules do I need? So actually, I find chemistry quite fun in the sense, you are a little bit like wizards. Okay, you are a little bit like ancient time wizards where you know, take one rock, take one wood, put together and then you form something new. Actually, that's what you are really doing in modern day. You are, if you want to know how to make something, you need to have the recipe for it, then you join them together, apply the correct conditions, and you get the chemical. That's what you will gradually do in chemistry. Daryl, yeah?
If we like send electricity to a resin container,
Yeah.
they can just vaporize without.
Not to my knowledge. How water is made, I do not think it is that way. Usually it involves a little bit of water to begin with to be present. There are actually many other ways to make water other than through what the method I just said. Yes?
Can we say slowly chemistry is like you take a rock, you take an axe, you take a stick, you make it into an axe. That's chemistry.
Okay, but you know what chemistry is? I don't know if you've heard the word alchemy before.
Yeah. Yeah, the bunch of we were so boilers. Alchemy is like
Okay, alchemy is just ancient chemistry. Long time ago, medieval time, they also have their form of chemistry. They'll be like, oh, if I take a rock and I take this rock and I boil them together, I'll get some other material. That is chemistry. It's just that in modern day, we are very sure what this rock is and what this rock is, and we know what the product is. Yes, Isaac?
So you're saying that electricity will like probably make like a water molecule, right?
Electricity doesn't make the water molecule. Electricity helps to facilitate the process.
So like let's just say like there's like a thunderstorm like out in the air. So every time when like it's dry, it will.
Actually, that's a good question. I don't know if water forms through that process.
That's how you do it.
But then once it falls, you'll
The rain that you see right now, it is not because thunder struck more than it's raining. It's not. Where did this water come from? Yeah, you learn, what you learn in primary school, water cycle. The water already exists. It's in your ponds, evaporates, then after it condenses down. Yes. With a very bright mind. Okay, I'm going to end the lesson soon because the assembly will start soon. Yeah? Hey, do you have key up, please? How are you going to do key?
Most likely the hall.
What?
Look,
Figure, yes. What?
I will use
That's what every alchemist is named for. If you want to separate water into there's no point. Okay, eventually, if you look at your periodic table, look,
potassium is K lah.
like my airways just suddenly clear. I suddenly can hear you all better. If you look at your periodic table, you'll find that, I don't know, if you go and give you a count, there are actually 118 different elements that we know of so far. Okay? Hey, yes, if you find another element, please let me know. Then I want to quickly get your signature. You'll confirm get a Nobel Prize. Okay? I will not dwell too far into this, but you can see that every element has their own symbol. And also they have their very unique name. Some of the names come from very ancient times. So I'll not spend too much time on this. We'll spend another lesson talking about the names of elements. Okay, so today I think we only managed to spend some time talking about the properties of elements. We learned that elements are pure, and one way to find out whether you have an element or whether it's a pure substance is if it has a fixed melting and boiling temperature.
Let's try mixing potassium with water.
And then put sand into the book with it.
If you go and research online, you mix potassium and water, it's one of those things that will cause an explosion.
Use lithium battery.
White phosphorus. White
Yeah, the
phosphorus.
lithium battery got more.
Hey, look.
Shall we watch what happens? Okay. Okay. Class, listen. Anyway, I don't want to leave you with a misconception to think that reactions can only occur between elements. That's not true. Right? Because actually reactions can occur between different between elements and compounds also. Here I have an element, potassium. Here I have a compound, water. You can also carry out reactions between elements and compounds. Let's watch the reaction. Okay, not all metals are hard. As you can see, potassium is quite soft. Potassium is a very soft metal. So here's a bit of potassium in water. Hey, what just happened? Oh, he ended up dying.
Yeah, to the guy.
Different metals, when you burn them, they have different colors. Yeah. You know the fireworks you see in the sky? It's because they put different metals inside. Each color you see is a result of a particular metal. So you got black color fire. I never see before lah. Okay, that's all for today.
They put
Let's stand by for
uranium.
today.
They put uranium.
Yes. Let me consider. Okay, it's okay. Just stretch yourself. Can you stop the video?